For this first part, we're going to look at actually evaluating some limits by looking at their graphs. This first limit says to find the limit as x approaches pi over 2 of tangent of x. And just a reminder from the unit circle, tangent is sine of x over cosine x. So sine is basically your y values, cosine are your x values, so tangent represents the slope of your radius. We know pi over 2 is up here. So we're going to look as we approach, as our radius comes up, what's happening to the slope from both sides. So if I look at the graph, I'm really interested in pi over 2. But I'm going to draw the graph from 0 and come in this way. So I'm coming in from values less than pi over 2, and from pi over here and coming in this way. So from pi and come in from values from more than pi over 2. So as we head towards pi over 2 and we look at each radius, you can see that they are all going up from left to right. So that means all of them have a positive slope. So our graph will be above the x-axis. And it's getting steeper and steeper and steeper, which means our values are getting higher and higher and higher. As we get closer to pi over 2, it's getting infinitely large. So I could draw the graph of tangent x like this. At pi over 2, we have an undefined slope, and that's where there's an asymptote. Coming in from pi, looking at this, you can see that at 0 and at pi, the radius has a 0 slope, so the value is 0. All of these radii are going down from left to right, so they are all negative. The graph will be below the x-axis, but they are getting steeper, so these are getting larger in magnitude, meaning that it's going from, say, -1 to -10 to -20. So as we get up here, again, it's getting infinitely steep, so that slope would be headed towards negative infinity. And you can tell that as we head in from the left and the right towards pi over 2, this graph is approaching two different heights. So the limit as x approaches pi over 2 of tangent x does not exist. And the reason is that the limit as x approaches pi over 2 from the left, and when you look at the limit as x approaches pi over 2 from the right, and let's call this graph f, of our f of x, these are not equal. So that limit does not exist. Now this is an interesting graph. So as x gets smaller and smaller and smaller, 1 over x is going to get larger and larger and larger. But you should know from the graph of cosine x that it's cyclical. It's periodic. It keeps going from -1 to 1, -1 to 1, -1 to 1, forever and ever. So the further or the closer you get to 0, the bigger this is, and the more our graph will actually oscillate. So if you graph it just on a standard graphing screen, all you see is the graph coming in, a little dip, something going on, and it going out again. If you zoom in, it comes in and it gets worse, oscillates, and goes out again. If you keep zooming in, it just oscillates more and more and more because you're going on the graph of cosine way out to the right. As we get closer and closer to 0, this gets larger and larger and larger, which creates the graph to oscillate more. So this limit does not exist, and you could say by oscillation, but it's just an interesting case to look at. Something much simpler, the limit as x approaches 2 of 3. So we would graph y equals 3. So horizontal line. And if we look when x is 2, it's at a height of 3, and if you come in at 2 from both sides, the graph is still approaching a height of 3. So the limit as x approaches 2 of 3 equals 3. It's the same limit as if x was approaching 0, 5, -1/16, 500, but if you're taking the limit of a constant, you're going to get back that constant because the constant graph is horizontal. It always has the same height. Which brings us to our first basic limit. It says let b and c be real numbers and let n be a positive integer. The limit as x approaches c of b, which is a real number, a constant, will always equal that constant. Now if you look at number 2, the limit as x approaches c of x equals c. So you could take c and plug it in for x and get out exactly what you started with, which should make sense. Limits are y values, and the graph we would draw of this would be the graph of y equals x. So when x is 1, y is 1. So the limit as x approaches 1 is 1. The limit as x approaches -1 is -1. So you can just take this and plug it in. Now what if that was raised to some positive integer? It says, notice n is a positive integer. Then that's fine. All of these are continuous. You can take c, plug it in for x, and you have c to the n. That's like saying the limit as x approaches 2 of x squared equals 4. Now this will work for any polynomial because they're always continuous. So I took a couple of problems and I want to show you how to break them up. First, what you hope is that you can just take this 2 and plug it in. So 4 times 2 squared is 4 times 4 is 16 plus 3 is 19. And the question is that really 19? Yes. You can plug into polynomials because they are continuous. Now, I wanted to actually break this down a little bit so you could see it. It's not so useful now, but it will be useful later. When you evaluate limits, you actually evaluate them term by term. When you looked at this, you said, oh, it's 4 times 2 squared, and then you added the 3. You looked at this separately. You can write it separately, which again, this will matter more later when you're actually trying to simplify limits and doing different problems with it. Another property you have is that this 4 is a scalar. It's just a coefficient, and it can come outside of the limit. So this is also equal to 4 times the limit as x approaches 2 of x squared. So we have 4 times this, which matches part 3. So you can just take the 2, plug it in. You've got that, times 4. And I could just, take out a 3, but there's no reason to. This is like our part number 1 here, where the limit of a constant is that constant. But the point here is that you can break it up into different ways to try to simplify these limits when they get more complicated. What you can't do is break up a limit when you've got some kind of grouping symbol over it. We all know that x plus 2 squared is not equal to x squared plus 2 squared. You can't do that. You can't distribute an exponent over a plus or a minus sign. It's actually equal to x squared plus 4x plus 4. You have to FOIL or multiply it in some way. This cube root is the same thing as a power. This is equal to the limit as x approaches 1 of 2x squared minus 10 to the 1/3. And just like you can't distribute here, you can't distribute here. But it's okay. For the cube root will be a continuous function, and you can just plug in. So if I take the 1 and plug it in, I have 2 times 1 squared is 2, minus 10 is 8. So this is the limit as x approaches 1 of, I'm just going to rewrite it the original way, the cube root of 8, which is a perfectly fine answer, of -8, I'm sorry. But you could also simplify it and say, we know the cube root of -8 is -2, because -2 times -2 times -2 is -8. And those are some basic properties of limits.